We're almost done. This is the last set of functions that we have to deal with. And then we've got the derivative of every function known to man. So there's 6 trig functions, so there's 6 inverse trig functions. We are going to need these down the road. They are weird derivatives, but we're going to at least build up a couple of them just so you can see why these are the way they are. Because if I just told you what the derivative of like arcsine was, there wouldn't seem to be any logic to it. Oh, let's review a little bit what an inverse trig function is. Y equals arcsine of x if x equals sine of y. So that's all that means. I don't use the notation sine with a little -1. I don't like that notation. It's not wrong to use. Your book probably does. But I use arcsine for the inverse of the sine function, arctangent, arcsecant, etc. This is what graphs of inverses look like. So remember from trig class, to get an inverse for the sine function, you have to restrict its domain. So you have to only consider the sine function between -π/2 and π/2. That makes a function 1 to 1, remember that term, and therefore invertible. So the red graph there is just that little chunk of the sine function that we're going to invert, and the blue graph is the arcsine function. So there's not much to it. That's the entire function. That's the entire graph of it. But you know from trig class that you need these things anytime you're going to solve a trig equation or undo any sort of a trig function. Okay, so that's a refresh on what it looks like. We're going to do the same moves we did with the logarithms. Since logarithms are just defined to be inverses of other functions, we can use what we know about the other function and implicit differentiation to get their derivatives. There'd be really no way to do this directly. You couldn't set up the derivative definition for like an arcsine function. It would be functionally impossible. Okay, so here we go. It's going to get a little mathy, but we're not going to do this for all 6. I just want you to see why these look the way they look. So if we say y equals arcsine of x, that's the function we're worried about, the inverse sine function. That's what we want to find the derivative of. So we want to find y prime, and we know we can do that with implicit differentiation. So just straight up by definition, x equals sine of y. So this is the same way we started when we did the logarithmic functions, right? So that's not calculus, that's just a definition of what those two things mean, and we're just assuming there are restrictions on this domain because of what it is. Here we go with the differentiation. The derivative of x equals the derivative of sine of y. The derivative of x is just 1. And remember, the derivative of sine of y involves the chain rule because y is a function. So the derivative of sine of y is cosine of y times whatever the derivative of y is. That's y prime because we don't know yet. That's the whole thing we're trying to figure out. So a little bit of algebra, solve that for y prime. So y prime is just 1 over cosine of y. And now we need to get cosine of y back in terms of x. We can't have a y in our final derivative, right? Because y is the function we're trying to find the derivative of. So to do that, we're just going to do a little bit of trickery. So we can always write sine and cosine in terms of each other with this identity. This is the most basic trig identity there is. No matter what number y is, what angle, whatever, we always have the sine squared of y plus cosine squared of y equals 1. That's true no matter what. It's the fundamental identity of trig. And we can always rearrange that little identity to solve it for either sine or cosine. So a little bit of algebra I didn't show there. If you just solve that identity for cosine of y, you get cosine of y equals the square root of 1 minus sine squared of y. That's the same identity. Convince yourself that that's true. Now, I didn't have to write a plus or minus to explain why wouldn't mean a lot to you. The way that we've defined these things to even say like y equals arcsine of x means that cosine of y cannot possibly be negative. So it just works out. Don't worry about it. So we're just going to replace the cosine of y in that expression for y prime with this. Y prime is 1 over the square root of 1 minus sine squared of y. And the reason we did that, remember, is we have to get everything back in terms of x. And if you look all the way back up to the top there, what is sine of y? Sine of y is x. So that denominator is square root of 1 minus x squared. And that's y prime. So that's the derivative of arcsine. So you see what I mean? It doesn't look right. It doesn't look like it has anything to do with the original function. It's not a trig function. We saw that with logs too, where the derivative is actually a different kind of function. So the derivative of an inverse trig function is this. It's something that looks like this. Okay, so new derivative rule. These are very hard to remember. If I taught your Calculus 2 course, I would not make you memorize these. I wouldn't make you memorize them in Calc 1. They're just hard to remember, and they're all kind of the same. And like I said, there's not a lot. It's not intuitive. So for now, you obviously don't have to memorize it, so keep it handy. But you do have to use it, and it is a weird one. So let's just look at the graphs. So arcsine is that green thing. It's just a little blip. It's just a little tiny function. The red thing is its derivative, that kind of rational square rooty thing. Notice the domains match. Think about why. Arcsine is stuck between -1 and 1 because sine, the range, is stuck between -1 and 1. And our derivative also is, because if x were bigger than 1, look what would happen to that denominator. Be no good. At plus or minus 1, actually, the derivative isn't defined because you'd be dividing by 0. So we have another case where the function is defined, but its derivative isn't because the function really kind of spikes right at those points. But except at those trouble spots, it's fine everywhere, so they share a domain. We're going to do the same thing with arctangent, and then we're just going to say, okay, here's the rest of them. And specifically arctangent, because it's a very unique function, and it's an important function in Calculus 2, because you'll see once we get its derivative, it comes up a lot when you're doing derivatives backwards, which we'll save for another day. Yes, you have to do that. So I'll breeze through it a little faster. We're going to let y equal arctangent of x. This thing's defined everywhere. So by definition, x equals tangent of y, right? Those are the same exact statement. They mean the same thing. That's how inverses work. Differentiate both sides with respect to x. Again, the derivative of x is just 1. To do the derivative of tangent of y, you have to use the chain rule. Derivative of tangent is secant squared, and then we multiply by y prime equals 1. Solve for y prime, so just divide both sides by secant squared of y. Y prime is 1 over secant squared of y, and again, we need to get that back in terms of x. So we need a different trig identity, and here's what it is. So one of the 3 so-called Pythagorean identities from trig class was this one. Secant squared of y equals 1 plus tangent squared of y. You have seen that. I know you've seen it. It's hard to remember. You may not have remembered exactly what it was, but that's one of the kind of fundamental identities. So we can just take that secant squared in the denominator and replace it with 1 plus tangent squared of y. And you'll see why I'm doing that in a second. So we got y prime equals 1 plus tangent squared of y, and then we just say, okay, but what's tangent of y? Where did we get that? What was that in the first place? We look back up, tangent of y is x, by definition, by the way we've set it up. So that whole thing is just 1 over 1 plus x squared. So y prime just turns out to be 1 over 1 plus x squared. And there you have it. That's the rule. That's the derivative of arctan. Again, I know it doesn't look right. If I just told you that, you'd probably take my word for it, but it does look weird, but it is true. That's the derivative of that function. It's not a trig function. Right, so arctan is the green curve. Remember, it's that thing that has 2 asymptotes and is defined everywhere. 1 over 1 plus x squared is the red curve. So just compare the two. Arctan is always increasing, so the derivative is always positive. Arctan doesn't have any maxes or mins, so the derivative is never zero. The derivative does have that spike in the middle. It looks like a bell curve. It's not, but it looks like one. And that's because that's the only place where arctan increases kind of fast. So the derivative jumps up there, but then it quickly jumps back down. And here they all are. So take a second, pause the video, write all these down, keep them handy. I think in the next video, we'll just summarize every derivative we have. So you should have them all in one place at some point. I would make your own. I wouldn't just print one off from the internet because it's helpful to make one of your own, and however you organize it is, you're going to understand it better. But here they all are. Like I said, I wouldn't ever make you memorize these. They're hard to remember. So arc cosine, the derivative is the same as arc sine, only negative. Notice arc cotangent, it's the same thing. The derivative of arc secant is even weirder. It's 1 over x times the square root of x squared minus 1. We could derive that the exact same way. We're not gonna. That's just what it is. And then with arc cosecant, it's just the negative of arc secant. So like when I memorized them, I just think of it like that. You just memorize the 3, then the other 3 are negative. So there they are. And that's all of the derivatives, right? That's every single function. So we did it. Let's just see some examples of these things in action. Let's do one involving arc secant because it's kind of weird. It has multiple copies of x in its derivative. So when you have arc secant in conjunction with the chain rule, there's going to be like multiple copies of the inner function. So the derivative of arc secant of 5 to the x, if you look at the derivative of arc secant, it's going to be 1 over, instead of x, it's going to be 5 to the x times the square root of 5 to the x squared minus 1 times the derivative of 5 to the x. Right? That's what that looks like, right? So you just take the derivative for arc secant, replace all those x's with whatever the original function is, and then move in 1 with the chain rule. And then the derivative of that exponential is just the natural log of the base times the function itself. So that'd be a fine answer. Yeah, right. It's weird looking, it's nasty looking, but it wasn't hard. We do have multiple copies of 5 to the x in here, so there's no reason not to factor it out, but you wouldn't have to. Again, to me, it just seems like common sense. So we have a 5 to the x in the denominator and in the numerator. So just take it out. And then the other thing I did is I just said, okay, 5 to the x squared is the same thing as 5 to the 2x. So it's not so much simplifying as it is just kind of consolidating and putting everything in one place. Okay, a little uglier. We've got e to a function. We got e to the arc cotangent of x squared. So actually 3 nested functions here, which means we have to apply the chain rule twice. So first you deal with the e to the, and it looks weird, but the derivative of e to the whatever is e to the whatever. So your first step in the chain rule, that first differentiation, nothing happens because e to the exponentiation is its own derivative. So then you just move inside and start doing the stuff in the exponent. So now we have the derivative of arc cotangent of x squared. So arc cotangent is negative 1 over 1 plus x squared. Except it's not just x squared, it's x squared squared, because x squared is that inner function. And then finally times the derivative of x squared, which actually is the first one we ever did, so you know. So again, just a little bit of consolidation. I moved the negative to the outside just because I think it looks nicer. I said x squared squared, you just multiply the exponent, so that's x to the 4th. So that'd be a fine answer. Again, this can't really be simplified, but it can be consolidated and just written in a way that's more kind of pleasing to the eye. So I think the most, to me, the best way to write that is negative. Okay, I took the 2x times e to the arc cotangent of x squared, and then just over 1 plus x to the 4th. So right, we're getting very different functions than we started with. Okay, if you can do this, you are in great shape. So I like to throw ones like this in here, not to like overwhelm you, but the opposite, to make you realize this really isn't that hard. And in fact, the way I've been doing it with like actually writing out the steps, it's almost easier once you get confident to just do it all at once. Like at some point, you should be able to just do this in your head, basically. You should be able to just write down the answer to this without showing any steps. Now, if you want to take the time to take out the steps and do it now, wherever you're at, obviously do. But once you do, you kind of realize that like every little step, like you can do everything in that step just in your head on the paper. So this is 2 to the sine to the 4th of e to the x times the arcsine of x to the 5th plus 6. So it's product, so we need the product rule. The first function, our f, is a composition of 4 functions, and our second one is just a composition of 2 functions. So we're definitely doing the chain rule within the product rule. And then the only thing is in that first function to make sure you know the order that you're doing things. So I'm not going to show any steps here. I'm just going to jump straight to the answer. But I'm going to talk through the steps right now and then jump to the answer, okay? So it's the first function times the derivative of the second function first. So you just copy the 2 to the sine to the 4th thing. The derivative of arcsine is 1 over the square root of 1 minus x squared. So then it's 1 over the square root of 1 minus x to the 5th plus 6 squared. And then times the derivative of that inner thing, which is just 5x to the 4th. So that's the first term. That's the first function times the derivative of the second function. And then it's plus the derivative of the first function, which is going to take some doing. So the derivative of the first function, the outermost thing is the 2 to the, is the exponential. So it's the natural log of 2 times 2 to the sine to the 4th of e to the x. The next function in is actually the 4th power. Remember, that's actually sine of e to the x to the 4th. So then it'd be times 4 times sine cubed of e to the x. Next function in is sine, so it would be times cosine of e to the x. Final function in is e to the x, which is its own derivative, so finally you'd have a times e to the x. And then we're still within the product rule, so then it would just be times the original second function, arcsine of x to the 5th plus 6. Okay? So you got all that? So here it is. All right, that's the derivative. And, you know, a couple of weeks ago, this would have terrified you to even look at. But don't let it. It's really not, this isn't the hardest math you've ever done. It looks like the hardest math, but it's not. Okay, so let me just rattle it off again. That's the final answer, and there'd be no real reason to try to simplify this. Okay, so it's the first function, 2 to the sine to the 4th of e to the x times the derivative of the second function, which is 1 over the square root of 1 minus x to the 5th plus 6 squared times 5x to the 4th. Product rule plus the natural log of 2 times 2 to the sine to the 4th of e to the x times 4 sine cubed of e to the x times cosine of e to the x times e to the x, then times just the original second function, which was just arcsine of x to the 5th plus 6. Okay, so that was over the top. But if you can do that, if you're even sort of comfortable doing that, you're going to be just fine for this next test. And I like to show you ones like this that are over the top, because again, it's not really algebra. You're not solving anything. There's no trick to it. You're just applying a bunch of rules. Just make sure you do them one at a time, and you just be really careful about the chain rule. Like with that sine to the 4th is the first thing you do. So don't forget that. And then you deal with the sine. And then you deal with whatever's inside the sine. So if you're just really methodical like that, you know, you can really, I know it seems weird, but you can do a problem like this really all in your head. And that's it. That's as hard as I promise it's ever going to get, at least derivative-wise. That's all of them, right? We have all of the rules now. So you should theoretically be able to do any derivative I throw at.